For decades, the standard model of Alzheimer's disease prioritized clearing amyloid or tau. In contrast, Dale Bredeson's RECODE protocol stabilizes the neural network by deploying multiple lifestyle interventions simultaneously. The 2014 case series and subsequent publications demonstrated cognitive improvements in small cohorts. By addressing diet, exercise, sleep, and stress at once, the protocol achieved clinical results that single drug trials have struggled to match. Despite these successes, the protocol lacks a specified biological bridge. It provides a comprehensive checklist of interventions without identifying the cellular pathways through which these diverse actions interact. This gap leaves the protocol's successes categorizable as anecdotal. Without a mapped biological framework, there is no way to accurately predict which patients will respond or how to scale the treatment for a broader population.
Bredeson identified the correct clinical phenomena, that Alzheimer's requires a multi-axis defense, but his protocol lacks the mechanistic blueprint to explain why these various changes converge on a single outcome. To organize his findings, Bredeson categorized Alzheimer's into distinct subtypes: type 1 inflammatory, type 1.5 glycotoxic, type 2 atrophic, and type 3 toxic. This categorization suggests these subtypes are distinct diseases requiring isolated pathological models and independent treatment strategies. The bioenergetic collapse thesis provides a biological map for these categories, showing how they relate to the cell's internal maintenance. These subtypes represent different upstream entry points that converge into the same downstream biological failure. The clinical differences between patients reflect the route they took to get sick. The final state of the disease is identical. That destination is the collapse of the integrated quality control network, composed of 4 essential nodes: mitochondria, lysosomes, the mTORC1 sensor, and the NLRP3 inflammasome. These operate in constant two-way communication. Intermittent fasting and NAD+ precursors directly strengthen these nodes, reinforcing their clearance pathways. Optimizing sleep improves glymphatic clearance, reducing the volume of extracellular waste the system must process. Managing stress lowers glucocorticoid levels, reducing the allostatic load that degrades mitochondrial efficiency. The multimodal approach targets the entire quality control system. By intervening at every node, the protocol prevents localized failures from starving the others of resources. Each subtype triggers this collapse by attacking a different node. Type 1 inflammatory Alzheimer's begins at the NLRP3 immune node, while type 1.5 glycotoxic cases attack the mTORC1 metabolic fitness node. Type 2 atrophic cases enter through a loss of trophic support, starving the network of growth factors required for maintenance. Because these nodes are coupled, the entry point is irrelevant. When a single supporting pillar cracks, physical tension transfers, triggering a systemic collapse. If the lysosomal node fails, mitochondria cannot be cleared. Without functioning mitochondria, the cell lacks the energy to run the acid pumps. They fail together. Since coupling pathways propagate damage universally, durable benefit requires rehabilitating the entire system, regardless of which node failed first. This brings us to the type 3 toxic subtype, the heavy metals, mycotoxins, and organic pollutants that often present in younger patients. These toxins drive the Panthos model of plaque formation. Inside the neuron, a lysosome fails to acidify, swells with waste, and eventually ruptures, extruding a dense core plaque from the inside out. Toxins physically attack this specific lysosomal and mitochondrial machinery. Mercury inhibits mitochondrial complex 3 and 4, collapsing the organelle's membrane potential and overwhelming the cell's ability to recognize and clear damage. It also disrupts the microtubule network used to transport waste. This creates an intracellular traffic jam, preventing damaged mitochondria from reaching the lysosomes for degradation. Lead accumulates within the lysosomes and directly alkalinizes the internal lumen, neutralizing the acid required to break down cellular debris. Ochratoxin A from mold physically jams the lysosomal proton pumps. This mimics the exact mechanical failure seen in genetic familial Alzheimer's. Persistent organic pollutants hijack the aryl hydrocarbon receptor, shutting down the brain's native antioxidant response. This creates a self-amplifying loop. Clearing these pollutants requires ATP and cellular energy, the exact resources the toxins have just destroyed. Toxin exposure does not create a completely different disease. Instead, it accelerates the age-dependent bioenergetic collapse by decades through direct physical-mechanical sabotage. Bredesen correctly prioritizes identifying and removing environmental toxins from the patient's environment. However, removing a toxin stops the ongoing attack, but it does not repair the machinery already broken by the exposure. Indirect lifestyle interventions often fail in these cases. If heavy metals have physically shattered a receptor, the signal from a ketogenic diet or exercise simply bounces off. This reveals a major omission in the RECODE protocol, the need for direct mitophagy induction to manually clear dead organelles. Urolithin A is a clinically tractable tool for this. It directly forces the PINK1 and Parkin clearance pathways open, bypassing the toxic damage to restore mitochondrial quality control. Reversing type 3 Alzheimer's requires combining toxin removal with active chemical restoration of lysosomal acidifiers and mitophagy drivers. Success also requires better measurement. Cognitive testing and volumetric MRI capture gross structural changes that occur too late in the disease trajectory to guide early-stage intervention. The necessary molecular readout is the health of the perineuronal nets that wrap around parvalbumin-positive interneurons. This can be measured in real time using gamma oscillation electrophysiology. It serves as a functional indicator of whether homeostatic microglial function has been restored. Bredesen provides the clinical architecture, and the bioenergetic collapse thesis provides the mechanistic specification. Locking them together transforms an empirical checklist into a reversal protocol.